Welcome to Net 204, Connecting Your Data Center to Cloud, Approach for Mission Critical Network Reliability. My name is Nicolas Cristofaro. I'm a customer engineer here at Google, specializing in Google Cloud Network. So first, let's talk about Google's network. So when we talk about Google's network, we're talking about a massive global platform, as you can see. 134 points of presence, massive investments in subsea cables, connecting the world, as you can see behind me, all within a private backbone network that we own or that we have private connectivity for. The map here clearly distincts some regions that we have, of course also future regions that we're planning to launch, as well as the mass point of presence that we have to connecting your data center to the cloud. So let's talk a bit about how do you connect Google to the cloud. So connecting your place to our place. We actually have 5 ways of connecting Google to the cloud. We divide these into 2 different sections, public addressing and private addressing. The latter at the top is the public addressing method, which is actually connecting Google via the various means of peering. So direct peering is one of them, which offers the ability to connect to Google via standard peering that you would do with an internet exchange, essentially connecting your public prefixes, so public address blocks that you would own, to Google Cloud via standard BGP peering. On the top right-hand side, we talk about carrier peering. Carrier peering is essentially the same means of connecting to Google via public addressing, however, through a carrier that provides that connectivity. So this is in case, for example, you do not have the connectivity to Google directly to be able to meet us at our peering facilities. You can do that through a carrier. On the bottom part, we speak about private addressing. Now this is really interesting for enterprise environments where you want to extend connectivity from your on-premise environment using private RFC 1918 addressing and connecting directly to Google Cloud. So that means being able to reach directly your on-prem workloads to Google Cloud via 2 means of connectivity. And then of course we have the VPN option, which kind of sits hybrid in the middle, which provides a mix of connectivity across public internet links to do the private addressing, extending your on-prem environment to the cloud. So when we speak of private addressing, we actually have 2 methods of doing this. One is dedicated interconnect, which is to directly connect to Google Cloud via one of our various points of presence. That means your equipment is co-located in a point of presence, or you have connectivity to our point of presence and establishing a dedicated link to us. The partner interconnect offering is actually to provide connectivity, again privately, however, through a partner, a service provider that is able to extend the last mile connectivity from your on-premise environment to Google Cloud. In case you do not have connectivity in one of our points of presence, you could use a partner interconnect to do that for you. And as a hybrid model, as I mentioned, VPN is a way to connect via public internet links, and often enterprises start that way before actually moving on to purchase a dedicated or a partner interconnect offering. And I'll show you later on actually how seamlessly the transition is done between a VPN connectivity to Google Cloud through a partner or dedicated interconnect link. So let's speak a bit about the Cloud Interconnect. But first, I'm pleased to announce that we are announcing 100 gig connections at our POPs. So now you're able to connect not only with 10 gigs, but now with 100 gig connections at our points of presence. So Cloud Interconnect, as I mentioned, is a method to provide access to private RFC 1918 addressing from your on-prem workloads directly to the cloud, and it enables essentially a hybrid cloud connectivity model. It does not require the use of management of hardware or VPN devices, because this is something that you directly connect your on-premise router to us via the various POP locations that we're located in. So from the left-hand side here, we see dedicated interconnect. As I mentioned, we could do 10 gigs. Now we can do 100 gigs. We can provide an LACP bundle, so a link group bundle from 8 times 10 gigs or 2 times 100 gigs for provided transport circuits directly to our cloud environment from your on-premise data center. And a partner interconnect provides dedicated bandwidth for sub-circuit rates, starting at 50 megabits all the way to 10 gigs, provided through a service provider network. So here's a bit about how the interconnect deployment looks like. So we can look at a dedicated interconnect in this way. We have a co-location facility in the middle. The co-location facility is essentially where you would meet us at one of our points of presence. So you may either have a cage already established in one of the facilities. For example, some of the Equinix facilities is a very common co-location facility, or any other co-location facilities. Or you can extend connectivity there through one of any kind of telco providers that can extend that connectivity to you. And from that, you extend your on-premise connection to your data center, and we provide connectivity to our cloud network. Now here's a list of our interconnect locations. So as you can see, we're present all around the world in all the continents, except of course Antarctica. And then we have connectivity with low latency links, which is the dark green circles, which are providing very low latency access to Google Cloud resources if you need a low latency access between your workloads and Google Cloud. So that means you can provide sub 5 milliseconds on average from these sites to any regions that are located in these points of presence. Looking at the partner interconnect offering, this is essentially a model where the partner is essentially providing the connection to Google. So partners have established a partner relationship with us already. They've established connectivity with us, and they provide that last mile connectivity to their clients. So various partners offer that. And if you're not looking for something at 10 gigs or potentially higher throughput, you would look at a partner to offer that because they can provide sub-circuit rates from 50 megabits all the way up to 10 gigs. So they can provide that solution. And also one thing that some partners are able to offer as well is that they can minimize the router requirements. So you may not need a router at the co-location facility themselves in case you want to do something like a multi-cloud scenario and want to connect cloud to cloud. Some partners offer the ability to connect two clouds together via virtual router offering. So let's look at some of the distinction between partner and dedicated interconnect. So why would you choose partner? Why would you choose dedicated? I talk to a lot of customers. Depending on their use case, it's very clear. Partner is where you're not able to have access to our points of presence. You're not physically co-located in a point of presence. You may not need to have a requirement of 10 gigs, right? You don't need 10 gigs, which is the minimum that we can offer with dedicated interconnect. Therefore, a partner will provide you a sub-circuit rate starting from 50 megabits all the way to 10 gigs, and we can provide that via VLAN attachments on our end. You pay only for what you need. SLAs require at least to have 2 VLAN attachments, which would terminate at 2 different availability zones within a metro area. If you want to have an SLA of 3 nines and then 4 nines, you would establish that across 2 different metropolitan areas. You can actually also establish with partner interconnect, you don't need to be within one org. We can actually extend the connectivity from multiple orgs because the partner interconnect VLANs can land in different organizational units within GCP. For dedicated, it's often used by customers that require high throughput. They require minimum of 10 gigs. The customer would essentially meet us at one of our POPs, or again, extend connectivity to one of our POPs, either via a service provider, or meet us physically in one of our point of presence. All the VLANs are actually riding on the same physical link, so that means that when you establish VLAN attachments through our cloud console, you would actually establish the VLAN attachments within the same physical circuit that's established with us. SLAs again require at least 2 connections to one metro area across 2 availability zones, and then all VLANs need to land in the same organizational unit in GCP for dedicated interconnect. That means that you can establish a project in GCP within one org, and that project can share its resources, but is still bound by the organization. That's one of the advantages that the partner interconnect can do, is you can actually span that across multiple organizations if you need to. So let's talk about a few different ways that you can actually use interconnect and some of the use cases that our customers are using today. So here's just an example again of the private routing that you can establish between on-premise and your on-premise infrastructure and our cloud environment. So essentially you would establish a BGP peer via our offering, which is called a cloud router, which would be deployed in the cloud region, and then establish BGP peering with your on-premise router and exchanging prefixes. In this case here, we have a headquarter with an external data center that has a network of 192.168.55.0/24, and we're advertising that to the cloud region, and the cloud region is receiving that prefix over BGP, and the cloud region has 192.168.49.0/24, and we're advertising that across. So we can establish that connectivity through the cloud router, which is our virtual BGP speaker in the cloud, and your on-premise BGP speaker. Another use case that we've seen is because of the concept of global routing and the concept of our global network, we're essentially able to deploy within one VPC multiple regions. So that actually allows you to connect with one router that you deploy in one region. You can actually reach natively other regions within GCP. So that means that we're able to advertise prefixes that would exist, let's say, in a different region than the region where the cloud router is deployed. And you can actually ride the backbone of Google's network to provide connectivity between these regions. You do not need to duplicate your effort in building separate cloud router instances in different regions. This is done natively through our global backbone network. It's a flag that's enabled in Cloud Router. When you actually deploy this, it's called global routing. It enables you to seamlessly transition our network and allow access to remote regions from the Cloud Router's region. DNS is another one of our very popular solutions as well. Customers would like to deploy on-premise. They have on-premise already a DNS server where they have host names that they're resolving for their private resources on-prem, and then they also want to deploy resources in the cloud. So they would use Cloud DNS in the cloud, specify specific A records for different VMs that they spin up within the cloud, and they would want their on-premise environment to also resolve host names in the cloud. So they would do that via DNS forwarding. We have both inbound and outbound DNS forwarding, which actually allows you to resolve host names from on-premise workloads to the cloud, and also from the cloud to on-premise workloads. And we can allow that through the means of interconnect. So via either a dedicated or partner interconnect, or through VPN, we're able to extend that connectivity via the means of DNS forwarding. Another great offering is through the shared VPC model. So within Google Cloud, we're able to deploy a model via shared VPC, which essentially structures a host project, which is essentially the anchor for all your networking resources within the cloud. So service projects do not need to worry about networking. They just need to consume resources. They can be development teams that just want to deploy applications. They don't need to know about the underlying networking infrastructure, the routing, the subnets, the firewall policies. This is all done by a centralized networking project that would be managed by generally a networking team within your organization. And that project would deploy Cloud Router within a region, and then that Cloud Router could essentially share the resources of the interconnect with the individual service project. So the service project would consume networking resources similar to subnets that you would grant them access to, and they can natively route with any routing that's available within the host project to your on-premise environment. So again, it really simplifies the model. You don't need to duplicate multiple interconnections in each project. You can actually centralize this, have a central network administration team that manages the networking for your environment, and the rest of the teams that need to manage development projects or other types of service projects do not need to worry about networking, and they're essentially connected back to your on-premise environment via policies that you set. Another use case is connecting privately to Google services. Google has many APIs that can be exposed, for example, cloud storage or BigQuery, that you may want to utilize from on-premise. And also because you have a dedicated link to Google, it's a good benefit to be able to use that link with low latency access, high throughput, to be able to store data to, let's say, a cloud storage bucket, or to load data into BigQuery services. So you can actually advertise via via VIP range back to your on-premise environment, that API that you can call, and then you can actually make calls to Google Cloud's API services that are available through this API. So this supports Google API endpoints. There's a subset of endpoints that's currently supported with this. And essentially on-premise, what you would do is you do a DNS change to rewrite the Google API's domain to use a specific VIP range that allows you to connect to these prefixes through an interconnect link. And you would advertise that prefix, which is, you can see in this example here, it's 192.168.153.4/30 on the Cloud Router back to your on-premise environment. So the Cloud Router actually allows you to program which routes you would want to advertise, and by advertising this range, making the necessary DNS changes, you can actually connect back to on-prem to Google API services natively. And let's talk a bit about high availability topologies. So one circuit, as I mentioned earlier, does not give you any kind of SLAs. To have an SLA, you need to have two circuits for redundancy. So in this case, we have a co-location facility which is located in one metropolitan area. That metropolitan area would have two availability zones. So to have any kind of SLA, a 3.9 SLA with us, you would need to connect across two of these metropolitan availability zones in a single metro. So with BGP Graceful Restart and Cloud Router, we're able to provide means of having high availability across these two zones. Now for customers that require very high availability, we would want to duplicate that effort across two metropolitan areas. So in this case, you may have a metropolitan area on the East Coast, maybe one on the West Coast, and you would be, again, connected across two availability zones within these metropolitan areas. And that would provide you a 4.9 SLA with us to connect back to GCP. And within GCP, you would deploy a Cloud Router in one region and a Cloud Router in the other region, generally as close as possible to where you are collocated geographically. So if it's on the West Coast, you would pick a region on the West Coast, and on the East Coast, you would pick a region on the East Coast. With the means of global routing, as I mentioned earlier, we're actually able to then natively transit our network in case of failure. So if we were to lose an entire region, we're able to route via the other region to connect back to your on-premise environment via this model of deployment. And now I'd like to introduce my colleague Sasha on stage to talk about high availability cloud VPN.
Hi, I'm Sasha. I'm one of the engineers at the VPN team. And if there is one thing I learned in my years working for VPN, it is that reliability is a critical feature of VPN. Because if your connectivity from your on-prem location to GCP is down, you'll feel it across all the organization. Now, the protocol that we use to run VPN is the industry standard called IPsec. It's pretty good when you consider its encryption capabilities, but its ability to detect and route around failures is not so good. So if anything fails on the way from GCP to your location, then your tunnel will be toast. And we want to build a more reliable connection. And to do that, the way is to use redundancy. So you can set up several tunnels running in parallel between the two locations and hoping that if one is down, the other will still be up. So that gives you some value, but that's not enough. Because if those tunnels share any component on the way from GCP to your location, if there is a fault in that component, again, your whole connection will be down. So not only you need to provide a redundant connection, you need to be able to isolate failure by making sure that at no stage there is a single point of failure in which your tunnel is working. Now, as being cloud, this is virtualized hardware, so where do you even start? So to do that, we developed a new VPN product called High Availability VPN. And for that, we have a new kind of cloud VPN gateway, slightly different from the old one. And what it does, it provides you with two interfaces. And you can think of them as two different network cards, similarly to the physical network cards you would put in your computer, so if one of them is burnt out, the other is still continuing to run your traffic, but this is virtual. So if you have two tunnels attached to two of the interfaces, we will make sure that they share nothing. They share no line cards, no network connections, no machines, no switches. Actually, being cloud, we are pretty sure that they will not even share a data center. So they are pretty much separated, and if one of them goes down, the other is still assured and very likely to be working. And then if this failure scenario happens, then a short time after that, the system will discover and that one tunnel went unhealthy and switch all the traffic over to the healthy tunnel. Now, how much exactly that gives you in terms of reliability, it's a good question. It's a function of how good is the isolation and how fast is the process of switching over from unhealthy tunnel to the healthy one. And we did this analysis for our system, and I'm happy to announce that we are going to provide 4 nines, which is 99.99 regional availability. So it means 4.5 minutes of maximum monthly downtime, or 53 minutes yearly. And just a few notes. So this is a regional product. You do not need to go multi-regional to have this level of availability. Just one region is enough. You will be able to connect just as with classic VPN that we had. You'll be able to connect both GCP to GCP or to your on-prem locations or even to another cloud. The only requirement that is mandatory now and was optional with classic VPN is that we need the VPN on the other side to support dynamic routing. If you think of it, it makes total sense because you want your system to be able to fail over, to switch the traffic from one path to another, so it's natural. And one last thing to notice is that when you're providing this redundant connection, you're actually having twice as many tunnels as you're assured to have in case there is any system failure. So if you watch the observable capacity that you have in your bandwidth, then it will be twice as much as you would have assured. And so if there is any failure, then your available bandwidth will go down by a factor of 2, and that's not the time when you want to discover that you actually needed more tunnels than you have configured. So to have a consistent experience of your bandwidth staying constant all the time, what we recommend is to set up a VPN connection in an active-passive configuration, meaning that one of the tunnels has priority, and all the traffic flows to it unless that fails, and all the traffic switches over to the other tunnel. With dynamic routing, again, that's easy to set up. You just use different MED values, and that's it. So to recap, we are going to provide 4 nines availability. This system is currently in alpha. It's going to launch to beta next month. And yeah, here's to more traffic running more smoothly. Nick, back to you. Thank you.
Thank you. OK, so putting all that into perspective now, I will actually go through a demo that looks at a common enterprise use case where we have an enterprise that starts with a VPN tunnel. Here, for example, I have a customer project. I have an IPsec tunnel connected back to a customer router on-prem. I set, as Sasha was talking about, the MED values, which are important in terms of traffic engineering that we're doing within the interconnect model. So in this case, I have a standard MED value of 100. And then I would like to set up another connection. This other connection would be a dedicated or partner interconnect offering. And then I don't want traffic to switch over to this connection, so I create a connection, create it with a lower MED value of 1,000, and I establish a link. Now, once that link is established, traffic will not seamlessly switch over yet because the value of the MED priorities are preferred over the VPN tunnel than from the interconnect connection. Now, to do a traffic switchover, it's very simple. We just switch the MED values between the VPN connection and the interconnect connection by swapping them, and then the traffic seamlessly moves over. So now I have a VPN connection that can be used as a backup. I can keep it online in case I need it, but right now my traffic would actually be routed across a dedicated interconnect or partner interconnect link. So here's a topology of what we're doing for this demo. So I actually have a HA VPN deployed with 2 interfaces. They're both deployed in active passive right now with MED value of 100, MED value of 200, so active passive on the VPN link. And then I have my interconnect links with higher MED values, 1,000 and 1,200. And they're connected back to an on-premise environment, which I'm running a ping test between that and a VM within GCP. So you can see here, I have, this is my cloud console with this project I just showed the topology. So we have here the interconnect session and the VPN sessions. You can see here the 1,000 and the 1,200 as advertised route priority. And we can see here the 100 and 200 for my VPN connections, my VPN tunnels. So here I'm running a ping test between the VM on-prem and then a VM, on-prem workload and then a VM in GCP. As you can see here, we have kind of sporadic pings between 20 to 30 milliseconds. This is running across the internet. This is a VPN tunnel. It's unpredictable due to the path nature of the internet. So I can't really rely on some guarantee in terms of milliseconds. It's pretty sporadic. It's flipping up and down. I want to now switch traffic over to a dedicated interconnect link to have higher throughput and also lower latency. So here I'm just running a script which is actually going to set the priorities, swap them between the interconnect and the VPN tunnels. And so really what I'm doing is I'm switching the priorities both on the VPN side in GCP, both VPN and interconnect side on GCP and also on-prem from my on-prem router to make sure that we're updating on both sides so that it's symmetrical traffic. Of course, it's important to do that so that traffic runs both symmetrically between the peers. And once that's actually completed, then we should see that traffic, the latency is going to be reduced quite significantly because we're going to go across a dedicated interconnect link with much lower latency and higher throughput. And as you can see now, We've actually lowered it down. Once it stabilizes, should be around 8-9 milliseconds when traffic is running across the interconnect. As you can see now, it's around 9 milliseconds, so that traffic seamlessly moved over to the interconnect link instead of the VPN tunnel. And as you can see, I've seamlessly transitioned traffic. There's no packet loss, easy to do. Now you can move traffic over and you have traffic riding across the interconnect link. And if we look at the cloud console and we refresh it, now we see that the priorities have been swapped. So the interconnect session now has 100 and 200. That's the preferred path, active passive path across the interconnect, and 1,000, 1,200 for the VPN tunnels. So they're still there in case we need it as a backup. In case there would be a failure, we can still transition traffic across the interconnect. So it's that simple to be able to do a migration between VPN and interconnect seamlessly between your enterprise and GCP. And with that, that is the end of my demo. I'd like to introduce Steve Olson from the Home Depot and talk about his interconnect experience. Thank you.
Thank you.
Yeah.
Hey, my name is Steve, but everyone calls me Steve-O. You'll have to excuse me. My voice is a little bit under the weather today. Caught something here, but we will push forward. I've been with the Home Depot for 12, 13 years, which means I'm incredibly tired and I've seen lots of different things. We like to say we've seen a lot of changes in Home Depot in the last 5 years, probably more than we've seen in the past 10 or 15. And that really goes to speak to our digital transformation, things that we've done. We've really put IT first. It wasn't always the case. When I first started, IT was kind of a backseat. Now IT is kind of a front seat driver, and we've really done this strategy called interconnected retail. And it's really an omni-channel strategy that lets our customers buy online, pick up in store, buy online, ship to their home, buy in the store. All of that kind of merges together to give the customer the choice. And one of that big strategies that we played first was the cloud. GCP we chose to do e-com for, and we have a journey that kind of used the tools that the guys have been talking about and how we connect it to GCP. But first I'm going to start with some base facts about Home Depot. I won't read everything on this slide, but Home Depot was founded in 1978. Last year we did $108 billion in sales. .com was up 22%, I think, in sales, and there's some .com guys here in front. I think in the last 5 years, 6 years, we've actually increased .com sales by $1 billion almost every single year. A lot of that growth has been in our cloud space. We completely re-platformed .com, and we'll talk about that in just a second. We have over 150 supply chain facilities. We have over 2,000 stores spread out across Canada, US, and Mexico, and of course 400,000 associates. What a lot of people don't realize is we do have a big IT presence. We have over 3,000 IT associates. We hired just under 1,000 last year, and we're still going. We have offices all across the country from our various brands that define Home Depot and companies that we use. And with that, I'll start with our actual strategy and how we started with the cloud. So what kind of led up to a distributed model for us is really just starting with e-commerce first. And around 2014, we completely re-platformed the website. And it was decided that we would go from an on-prem model to in the cloud. And some of the reasons are the classic reasons that you would hear, right? We were building our on-premise infrastructure for sales that would be around Thanksgiving or Black Friday or Father's Day. And you build this infrastructure to the point where you're using it for those days only, and then the rest of the year it sits stagnant. So we really wanted a more on-demand infrastructure that could scale. And of course the cloud came into that. It took multiple years to do. Really, this is going to be a condensed timeline, but I'll explain exactly how we got there. One of the first things is data movement, right? How do we actually get data from our on-prem to the GCP cloud? And the first thing, of course, is before we even get going with lots of projects is just the basic internet, right? So we have basic proxies and internet, and that doesn't scale incredibly well. What if you need private services, just like they talked about in the slides before me, VPNs and interconnects? We first started using VPNs, and I've kind of got a love-hate relationship with VPNs. Some people like them. I hate VPNs, and I'll explain that for a few reasons. I mean, VPNs suck, let's face it. But if that's all you can do, that's all you can do, right? We actually use static routes There was no cloud router at this point. This is around 2015, so we were stuck with static routes and no redundancy. And it worked, except it terminated on-prem here, and then it terminated inside the cloud. You know, it basically did what it needed to do, but we needed something more robust and we needed to scale higher. And so the problems with VPN, which I said we'll talk about, MTU. How many of you have ever dealt with frame size issues and MTU problems with VPNs? Like, yeah, everyone's hand's going up, right? MTU is a terrible thing to deal with, and it's not Google's fault, but Google, you have to have fragmentation before encapsulation. And if you've ever dealt with firewalls and packet captures and wire captures for why something doesn't work, does your application even support fragmentation? Does it know it's going to be fragmented? I just need an advocate just talking about it. We dealt with that so long that we needed to get rid of that. Speed and latency is another big thing. And one of the big things that I found about speed and latency is that if you talk to your customers, sometimes they don't know what the difference between that is. They might say, I need something quick, but does quick mean I need to load a terabyte of data in a day, or I need a connection to a database in 5 milliseconds? Sometimes you have to actually lead that conversation there to see exactly what they care about. Right? SLA and the internet in general, that's a big thing as well. You'd come in one day and your connection across the internet is 30 milliseconds, and the next day it's 45. We've all dealt with that. We actually made a diagram that basically showed cold potato, hot potato routing to explain to our application developers and our consumers what it's like that, yes, we have internet connections to the cloud, but we don't go straight there. I don't own the infrastructure in the middle. And getting their heads wrapped around the fact that, yes, I may leave here, but I don't know what some tier 1 provider does with it after the fact. And that's how we explain that to them. So let's deal with the VPN issue first, right? So we really wanted to have a way to have the VPN be better. We couldn't fix the MTU immediately, but we could fix some of the speed and latency problems. So this is where we really started discussing peering facilities. So we actually came up with, if we could get the VPNs closer to Google, we could actually get performance better. So speed, latency, reliability, SLA. And so we came up with peering centers on the east and on the west coast. Those were the first good choices because a lot of the infrastructure for things that we're using are there. And we have well-defined latencies now. So instead of using the internet, we own these private circuits between some of our data centers directly to these peering centers. So I can tell my application developers and all my teams, I know what you're going to get from a latency perspective. I know this is 15, I know this is 40, and we don't have to worry about the internet. So what we really did is, revisiting the first slide, is we moved the VPN connections all the way out to the colo there in the peering centers, and the VPN's still inside the project. So the internet's not used, right? But reliability and SLA go way up. Speed is now actually even better because now we have direct connections. So we're running the VPN basically on the last mile. We're not running it across the country and hoping that it gets there. We have our own private circuits that gets us there, right? So the real redundancy actually still isn't here yet. So we actually started doing multiple VPNs, but without cloud router and static routes and trying to scale that, that didn't work either. So we needed to do something even better than that. Right? It actually worked well enough that we basically started adding more. People liked it so much that we added a couple more. So now we have 7 milliseconds and 3. And we actually have vendors and application owners that test this and can get connections straight to GCP within 10 milliseconds. All right, so once we started doing that, thought, well, interconnect beta started, and if we could get the interconnect on, we could get rid of the VPNs. All right, so now we're going to fix the VPN issue. That's still a problem with the MTU. So what happens is the interconnect beta comes, cloud router comes, and we have now an interconnect plus a direct connect. So at each of the peering facilities, we have 4 different cables. We have 2 for public access, 2 for interconnect, and depending on what the project needs are, they can do private access or they can do public access over our own infrastructure to get there. The internet's not involved. And of course, with dynamic routing, the redundancy is much more seamless and the fails are much easier. So with that, we basically grew even more. We actually added another facility this year, and all these sites back each other up. They were talking about mission critical reliability. We built this in such a way that when we have circuit issues and some of these go down, our application owners don't even notice. Because if they're multi-region and multi-attached to different interconnects and use cloud routers, it automatically fails over. All right, so that's, we've scaled to there now, but we're even adding more. And really, it's not just GCP either. The journey to actually getting us connected directly to GCP led us to other things. We're using it for other providers as well, and other vendors and partners of us, and even the internet itself. So just the concept of getting to GCP led us to this distributed, regionalized network that we can use, and with a combination of new technologies like SD-WAN and things like that, we can have our remote sites, our stores, our distribution centers, we can have them all come to the closest peering facility and use cloud services or use the internet and things that they might need. They don't need to come back to the main offices. They don't need to go directly to the internet. We can control that all in a centralized, regionalized manner. And so, with that being said, what we're doing next is we're investigating what they talked about in the last few slides is private services via these channels, meaning using our private space to contact BigQuery and things like that. We're really interested in shared VPC, and we're going to continue deploying more peering centers and keep using the multi-region model and cloud routers and interconnects. And we'll probably even expand to more peering centers in Canada and Mexico this year. This model has proved extremely well. Our customers like it, and we will continue to do that. With that being said, that is my talk.